and away we go. I'm going to turn it over to Maria to run the show. Launch us off, Maria.
Thank you so much, Kimberly. Before we begin the event, I would like to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit River. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. We would also like to encourage our audience, depending on where you are currently located, to take a moment to acknowledge the place you're working from and the history of that place. It is my pleasure and honor to be welcoming you to this event and to be hosting it, which is not only an incredibly exciting conversation that I cannot wait to have, but also the first in the dialogue series events that we are launching this year, starting with this one, organized from the Robotics Institute. With the dialogue series, we're aiming to create a new space that encourages conversation, encourages critical discourse and discussion, productive dialogue, and hopefully some space of vulnerability and exchange of ideas around, with, within, and in robotics. My name is Maria Jablina. I'm an assistant professor at the Daniels Faculty of Architecture, Landscape, and Design, and a faculty member of the Robotics Institute, both located at the University of Toronto. And I will be your host and moderator for today. Before I introduce our lovely, lovely speakers and pass the stage on to them, I would like to mention a couple of kind of housekeeping things. As Kimberly has already mentioned, this event is being recorded and streamed to YouTube Live. So if you are not okay with your face being there, feel free to, turn your camera off, feel free to keep it on, however you would prefer to interact with the platform. The event will consist of short presentations from both of our speakers, followed by a discussion moderated by myself. If you as an audience are interested in participating in the conversation and asking questions to our presenters, I would really, really encourage you to do so, because that is the point of the dialogue series. And also I would encourage you to use all available features, including chat. I might also ask you to actually unmute yourself and ask your questions live, and we'll kind of figure out a good mode for us to interact from there. That is the housekeeping, and it is my pleasure to actually introduce our speakers today. The speakers are Brian Wingley, who is a construction technologist at Boston Dynamics, where he promotes new value-add autonomous capabilities for construction project delivery and works to expand the construction application ecosystem with a Spot SDK. Prior to Boston Dynamics, he was a senior construction automation researcher at WeWork, where he managed the construction robotics research program and contributed to initiatives in design automation, utilized prefabrication, and construction site progress monitoring. He has also taught architecture courses for many years, most recently at Pratt, where he led seminars in computational fabrication and industrial robotic automation for industrialized construction. Our second speaker today is Catherine Dorfler, who is an assistant professor for digital fabrication and leads the augmented fabrication lab at TU Munich in Germany, where she investigates the reciprocal symbiosis of humans and machines in architecture and building design. She holds a PhD from ETH Zurich and Gramazzo and Kohler Research Group and NCCR Digital Fabrication, and a Master of Architecture from the TU Vienna. So as you have probably guessed already from these descriptions and from the theme of today's conversation, we will be talking about robotics from within the field of architecture and construction. We have these two incredible speakers, one from more of an industrial background, one from more of an academic background, and I'm super excited to actually observe the conversation between them. And without any further ado, I'm going to pass the stage on to Brian, who is going to share his presentation with us.
Yeah, thank you so much for the introduction, Maria, and good to see everyone. So as Maria mentioned, I'm the construction technology manager at Boston Dynamics, where I manage Spot applications for the construction industry, which also includes architects, engineers, and real estate professionals. And prior to this, I was a construction automation researcher at WeWork. So I come from a kind of hybrid design and construction background. So the context of this talk will, of course, be about the way that we use Spot for construction and real estate applications. Of course, Spot is used across many industries, but we found a few things that are particularly valuable in dynamic construction environments. So a little bit of background that may or may not be necessary, but I like to just give a little intro about the company and what we're working on. I think we're best known through our YouTube channel. That's how most people learn about us and the work that we're doing. We have 3 primary robots that we're working on today. We have Handle in the logistics space. I call it the ostrich. So that is for dynamic picking and placement in factory and logistics environments. We have Atlas, which is our R&D humanoid or bipedal robot. That's the one that does backflips, parkour, and more recently dancing. And then we have our generalized mobility platform, which is Spot, and that's really what I'll be focusing on today. In terms of the Spot project overall, the first quadrupeds came out of the lab with the Big Dog project in 2004. And then it was later under the ownership of Google that there was a miniaturization of that form and that morphology to go into domestic and other human purposed environments. First was Spot Classic, which started in approximately 2015, through Spot Mini, which was a slightly smaller version and the first time that the full body manipulation capability was added with the arm. And then to Spot as we know it today in 2017. So I'd like to talk a little bit about what it means to have a robot as a platform versus kind of an end solution or product. And we really try to, do both simultaneously, to be honest. What makes Spot valuable is a combination of things. The means of locomotion and the dynamic systems therein create a way to move sensors around environments where that had previously been not feasible. So with my experience as a construction automation researcher, I started with drones, I started with wheeled vehicles, and I started with tracked vehicles to try to get sensors throughout my construction environments. They all failed at some point or another, some more gloriously than others. And I went from, initially putting out a report in 2017 that said legged robotics were too exotic for this purpose, to by the end of 2018 being convinced that legs were the only means of locomotion to be able to get sensors anywhere I needed them, specifically in interior commercial construction environments. So my mind was changed pretty quickly through about 1.5 years of testing. We know that just dropping a robot into an environment is not going to solve anyone's problems or add value. So we knew we had to bootstrap the technology on top of the robot, or as we call it, the payloads. So we started with sensing payloads with cameras, computing payloads with the Spot Core CPU, and manipulation payloads, which have been in development for years, but recently became commercially available this year with the Spot Arm. And then the GXP is to just create some customer-ready power and data connections from Spot's ports. We also know that it's important to be compatible with an ecosystem of sensors that people are already using in this environment. We do not need to reinvent 360 cameras. We do not need to reinvent laser scanners. So this is an example of how someone could configure a Trimble X7 3D laser scanner for site surveys with essentially any other Spot configuration. The big part of the platform, and when we released it, was, I think, in the beginning of 2020, which was to say there's an SDK. We are not going to anticipate every way that you're going to use this robot. We need to make something that's robust and flexible for you to build your own custom applications. So it spans everything from customers who actually want to rebuild certain components of the existing system, like mission control software and the autonomy stack itself. Customers who come up with interesting uses of the data that Spot captures as it maps its environments for autonomous navigation. But by and large, I'm dealing with customers who want to connect the robot into some kind of existing workflow or data ecosystem in construction. So attaching their favorite sensors like laser scanners and cameras and having those be able to be triggered autonomously in the context of a mission, or connecting the robot with cloud storage and or downstream software applications to contextualize the data that they're collecting and to make sure that they're not just automating the capture, but also the transfer of that data to the stakeholder who needs it. Big news for us this year was that we finally got recharging with the dock. So the obvious thing here is you surpass the necessary user intervention every 90 minutes to swap out the battery. But I actually think there are a couple other things that in the long run are maybe even more critical than that. One is that you get a gigabit Ethernet connection, so you can download very large files. Communication networks on job sites are extremely restricted. If you have a data capture robot and then you can't get the data off of it except with manual download at the end of the day, that's a problem. So we needed to have a means where lightweight data could be transmitted wirelessly with the right setups, but ultimately we knew we needed some kind of hard Ethernet connection to be able to download things and upload things like laser scans and 360 video files, which are very popular data types in construction and very heavy ones. And lastly, this gives you a robot that's always on and always awaiting commands, whether it's to start a scheduled autonomous mission or to use human operator intelligence to teleoperate through an environment and run an inspection. So a few common questions I get when I'm presenting this, bear in mind that part of my job is essentially to be a robot salesperson. So I get a lot of questions about why now and why is this valuable? We think that there are several parallel developments, the 5G with an asterisk, because that is taking a very long time to roll out, I think, in a usable way by most people. But nevertheless, the miniaturization and portability of sensors, as well as the reduction in cost, edge compute, and having access to downstream AI and ML tools, whether you're running those on board or in the cloud to process the data you're capturing, starts to open up this opportunity specifically for a capable robot platform to complete that autonomous field capture technology stack. And then the other question is, there are other ways to capture data. Why would I use a legged robot to do this? And I have some, responses to that on the right. I like to show this picture because I actually took this picture myself from hundreds of miles away, sitting at my kitchen table in a facility in Boston, and I'm in Brooklyn, by wirelessly, undocking a robot in the facility, walking up to this gauge, and then using a pan tilt camera and zooming in and capturing that image so that I could report the PSI. This, of course, was part of product testing, but it was in a real customer environment. And I was able to get the data I needed remarkably easily. It was an interesting experience too, because while I had been with customers on sites, the focus has largely been on repeatable autonomous missions. This was one of the first times I was using our new teleoperation platform, Scout, which I'll talk about a little bit. And I kind of forgot that there was a robot there, which I thought was a kind of a beautiful thing. It felt like not perfect telepresence. Of course, we still have a long way to go, but it was kind of a remarkable experience in the sense that I forgot that there was a robot that was facilitating this interaction. But more to the point, the reason we use robots is because people are too important for these tasks. In my prior job, we surveyed our construction superintendents and assistant supers about what we could automate for them to make them more productive and make their jobs, better, essentially. And they all responded that the daily site walk, the daily photo documentation exercise was something that was boring, that was hard for them to fit in, very difficult for them to do on a repeatable basis, the same photo at the same location at the same time, day after day. And they really needed to be doing other things at the end of the day. And they also just wanted to get home to their families. So that's really where the focus was, and that freed them up to do more valuable things. And frankly, humans aren't that good at repeatable data capture anyway. So it's kind of the perfect application for a robot in these environments. Fixed sensor systems, there are some that are valuable that are emerging. This isn't a wholesale dismissal of them. the issue really becomes that the operators of these sites, or these general contractors who are building these sites, they don't want to invest in a large number of fixed equipment and infrastructure for what is essentially a temporary environment during construction. And then lastly, as I mentioned before in my previous trials with other types of locomotion and robot morphologies, there just isn't another type of robot that's able to navigate stairs, climb up and around obstacles, walk on rebar and decking, wade through standing water the way that I've personally witnessed Spot do time and time again on a construction site. I will put an asterisk on this. I'm a huge drone fan and very bullish about the continuous advancements of drones and their adoption in the construction industry. I do think we will see more capabilities of drones to move into these types of challenging interior environments in the future. But as things stand, there are a number of limitations there that make a ground robot more sensible. So I like to talk about the interfaces, because part of this talk is really about how people interface with the robot. And it's not a cobot. It's not something, it's still an industrial robot. Like, you shouldn't be, patting Spot on the head or touching it, although many people do that and then put videos on the internet, which, stresses me out. But you really need to give Spot space. Part of that is safety, and part of that is also so that you're not blocking its perception systems as it's attempting to record the environment and build maps for autonomy. But the default way to use the robot is through a tablet interface, very similar to how you would operate a drone. And in the goal is the same there too, which is that you do not have to be a roboticist to record and play back autonomous missions. And this is what customers on construction sites are focusing on. I want to record a path through my environment. I want to record a set of actions to do in that environment. That could be a laser scan, taking a photo. It could be doing a dance, honestly, really whatever you want the robot to physically do in that space. That gets saved as a file that you can then play back day after day after day to get that repeatable autonomy while the robot exhibits obstacle avoidance and then kind of increasing ability to deal with an ever-changing environment. Construction sites are impossible nearly for this type of autonomy, and therefore it's actually a really great lens by which we can evaluate the performance of our autonomy systems. And I totally forgot to be playing this video while I was running my mouth, but there you can see a little bit of a preview of what's going on in terms of Spot building its maps and going from kind of node to node or waypoint to waypoint. You'll see as the video progresses too that it's building other types of maps as well. It's modeling obstacles, it's modeling the terrain. There are a lot of things, one of the things that we're often talking about is, well, can I do offline path planning? And the customers that we deal with want to do that from model context. They have things like building information models. There are a couple issues with that. Mostly not trusting their models. These are design intent models. They're not really fully calibrated with reality. But one of the things we've found, and that is just part of the culture, is nothing beats putting the robot in the real physical world and learning from the real physical world. So while there are other ways to program autonomy, you can certainly program missions offline with the SDK and do path planning, et cetera. The primary mode of operation is that the human is using their intent to walk the robot through the space, and that's what gets recorded and played back. And a big part of that too is indicating where it's okay for the robot to go. This isn't a harmless Roomba that's just going around and kind of vacuuming all day. This is a data capture robot in a hazardous and dynamic environment. While we could explore, so to speak, with the robot to build maps, you don't really want to have an industrial robot exploring a construction site. That's not safe, and that doesn't fit into their concept of operations. For those customers, typically customers not in construction, but in fixed industrial environments, the focus is much more on robust teleoperation and remote inspection, typically of hazardous environments, hard to access environments like oil rigs that are offshore, or just to be able to run inspections or check on things in off hours so that you don't have to physically be at the facility. This requires a communication setup that is frankly impossible right now for a construction operator to have. And while I think there's value here and overlap between what we're doing with Scout and advanced teleoperation and the repeatable autonomy that customers want on construction sites, there kind of tends to be a line between those applications. In terms of other ways that people can interface with these robots, on the left, you just saw gesture control. We have customers and developer partners who are all coming up with, surprising and interesting ways to use the robots. And that's great. We're going to focus on what we think are the primary interfaces, ones that we think are safe and valuable and make sense for us to support. And then we're going to let our customers come up with other types of interfaces. And many of these customers are also looking to add value to the robot, sell their own services, or in some cases even resell the robot with integrated technologies. One of the things that I really like about the development of new interface paradigms is it actually points the way to the ability to use multiple types of robots in an environment, or heterogeneous fleets. Spot is a data capture robot, and it's not performing construction tasks. So nor do I think that it's necessarily the right morphology for that versus, say, the Canvas robot for drywall finishing, or the Hilti robot for drilling, or the Dusty robot for layout. We're seeing the emergence of a series of task-specific robots with particular morphologies that are just really good at one thing, and then platforms like Spot that are kind of doing generalized things like site data capture. And I think you'll need both on site. And part of having both on site means that these robots need to interface with one another and be networked with one another. This is something we did in March of last year, just as a proof of concept between Handle, our logistics robot, and a ClearPath Auto AMR, where these two robots are directly communicating with one another. We've continued to develop protocols for that, as well as for path planning and simulation in the logistics and factory space. There will be more announcements on that publicly coming soon, but for now, this has been research and development in that space. So I'm going to talk a little bit, in closing, about what we're actually doing. What are some of the use cases we're seeing in construction specifically? The first time that I saw a robot in a data capture context was on Takanaka and a few other Japanese contractors' sites. I love this too because these are the same Japanese contractors that were doing some of the original work for task-specific construction robotics, or single-task construction robotics, in the 1980s. So it's interesting to see them continue to innovate, but this time with the adoption of Spot for data capture. And that's what caught my eye and made me realize that this was perhaps a feasible way to achieve these things on construction sites. So we knew that the SDK alone wouldn't drive adoption, that we had to have partners in the ecosystem. So the very first thing we built was a connection to an application called HoloBuilder, which allows you to contextualize the data you capture into blueprints. It's interesting to me that the first choice was to go with a 2D application versus like a 3D environment like BIM. But there are a lot of business reasons that that's the case. One of them is that a lot of general contractors do not coordinate in BIM. BIM had not survived that particular scope of the contract. This is a business problem that exists in the industry. It's not really for a robotics company to solve. So we need to figure out how we're adding value today as we also aspire toward more BIM-centric workflows in the future. Here's another example of something that doesn't require BIM, but kind of gives you a 2.5 dimensional environment by reading depth data from 360 video capture and using that to do 3D reconstruction via photogrammetry. It's something we did with Drone Deploy. What I love about the Drone Deploy integration is that customers that already had robust data capture programs with drones were also looking for ways to use ground vehicles or robots to capture data, and they wanted all of that in an integrated 3-dimensional environment. So people walking around, ground robots, drones, all of that going into one consolidated environment. So I think that's what the beauty of that particular integration is. Outside of the 360 image and video capture, laser scanning is hugely popular as something to automate with the robot. It's painful to plan for, it's painful to go out and perform the capture, and it's painful to process the data and get it to the stakeholders. So it's something where there's a pain point essentially every step of the way. But when we first worked with Foster and Partners, it was really about saying we work in 3D with BIM. We need a way to continuously check the reality, the construction site data, the progress, so to speak, with the original design model to make sure that those things are aligning. It's really a quality control exercise. Going beyond that, in terms of what other opportunities that data has, is if you put a laser scanner on a robot, it makes it easier to scan. Now you can potentially scan all the time, as opposed to just doing it once or twice for due diligence or for the creation of as-builts for the owner. So now I can use it to intelligently connect features of the point cloud with elements in BIM to do automated reports. Was everything placed? What percentage of drywall was placed? Was it placed on schedule, and was it placed without any clashes? So that's something where we started to notice there were other software applications downstream, like Avir, that were providing this service. Because today, BIM is not designed for the regular ingestion of reality capture. This is an opportunity for tomorrow, and this is an opportunity that is in part accelerated by the introduction of data capture robots onto the construction site. This is a very confusing diagram that will only make sense to people who are probably more in the know for the construction ecosystem. But what I like to point out here is I found this diagram on the Avir website as part of a blog post by their CEO. I think it's a great blog post. It's their most recent one, and it makes a lot of sense. And it's really about it's really exploring the point of data capture and how the point is to get analysis and insight and to move from capture to act as quickly as possible. I did some edits on the right to show that, it's a different scenario. And what really matters when you're using a robot is, are you coordinating in 2D or are you coordinating in 3D? They both have similar opportunities, which is the automation of progress quantification for a variety of purposes, to speed up payments, to manage the site, to catch errors. But they manifest themselves in different ways that I think are interesting. In the case of 3D coordination, you want 3D data, like point clouds. Point clouds are registered typically by the same software that runs the laser scanner. Therefore, the capture and contextualize steps are the same. And then you're looking for other solutions typically to do the analysis to be able to act on that. If you're coordinating in 2D, which by the way, it's about 50-50 with our general contractor customers, which is why this distinction is so important to me. The capture is just done with a camera that doesn't have any bearing on the rest of the process. But then the contextualize and analyze parts have been kind of collapsed into the same system, because all of the applications that allow you to pin 360 imagery or data to blueprints or sheet sets are also developing their own proprietary AI mechanisms for reading pixel and depth data from that 360 imagery and video data, and then to turn that into markups on the sheet that tell you the progress that's been made. In one sense, it's an extremely perverted use of technology to have advanced AI in two-dimensional blueprints. It is a bizarre mix. But on the other hand, this is what adds value to the customer today. So that's why I like to be aware of both. I think ultimately everyone wants to move into more of a 3D context, but there are a lot of disadvantages to that, particularly for customers who are not coordinating in 3D. It doesn't make sense for them yet. So you really have to deal with the realities of the industry. Here's an extremely confusing flow chart to talk about how all of this is dependent on the ability to have communications in a job site. So it's not just about, again, dropping the base robot. You have to understand, does this environment require LiDAR for enhanced perception? Do I need public LTE because I can't rely on my Wi-Fi network on site? Am I going outside and therefore I need GNSS? Am I going underground and therefore I need a mesh radio network? You can start to see that it's not a simple story to tell when you're introducing robotics into the real world, because there are a lot of dependencies for navigation and communication that are critical. It's also not a particularly easy story to tell in terms of, does the customer want autonomy or teleoperation? Am I trying to remotely inspect my environment, or am I trying to run routine autonomous missions? There's also nothing preventing you from doing both, from using teleop to record and play back an autonomous mission. But you have to understand those two kind of distinct paradigms for operating the robot. And then you have to understand what you as an operator are doing. What is your concept of operations? Do you want to follow the robot around? Usually not, maybe when you're first getting started, but there's not a lot of value in that. Do you want to be on site doing other things while you're running the robot? Or do you really need to be off site in some kind of centralized command and control area, or in the job site trailer, or back in your office while the robot is on the site? So, I could probably talk about this slide by itself for 60 minutes, but you can start to see that when you sit down and you talk with somebody about how these robots add value in their construction environments, it can be a nuanced conversation. And part of my job is to try to clarify all of those things and make them easy to understand, because again, we don't want our customers to have to be roboticists or IT specialists or communication specialists. We want to be able to provide a robotic product in the real world that they can buy and get value from fairly easily. So I think I'm going to stop there, because the next one gets into kind of a sales pitch. Plus, I think I've taken most of my time. So I'll go ahead and end there.
Thank you so much, Brian. This is a lovely look into somewhat maybe behind the scenes of what we see on and around a lot of the Boston Dynamics videos and spot conversations. I would suggest that we move on directly to Catherine's presentation, and then have more of a general discussion after both of our presenters have had an opportunity to speak about their work.
Cool, sounds good. I'm gonna share my screen with you. I also have to manage move all of the black boxes out. Give me a second. Do you still see a black box?
I see the green, your screen sharing. I think if you grab it on like the green part of it, if you grab that and just drag it to your other screen, that should work.
Ah, yeah, no. I think I can only put it at the very bottom. Is it still kind of there?
It's there, but I think that's also not too
Yeah.
big of a problem.
Okay, good. Okay, thanks, Maria, for the invitation. I'm super happy to be here, and thanks for the nice talk, Brian, and very insightful talk already. I want to welcome you very much to my talk on the topic of human in the loop, and how human-machine collaboration could shape the future of digital design and fabrication. One moment, I think I know that I haven't pressed the share sound button. Okay, now it should work. I want to start with a little video compilation of 3 projects during my PhD project at Grammaticola Research at ETH. My PhD mainly dealt with the topic of bringing robots out from the lab directly onto building sites, so having them build stuff on site. And this video compilation, I tried to point out on one common feature, and as you will see, this is not mainly concerning the robot so much. Can you hear the sound, by the way? And I wanted to put maybe a bit of a provocative question at the very start of my talk, mainly concerning if the task distribution between humans and robots, as we have seen in this video, where people are basically feeding material to the robot and then the robot places the material, if that is the ideal task distribution between humans and machines, or can we somewhat do better? And the question is if there can be other reasons or benefits of embedding human cognitive skills into digital fabrication processes. And also at which stage of the design to fabrication process this is best, either during design, planning, or execution, or a combination of these. Today's machines are not purely mechanical, but they are reprogrammable digitally. They can be connected with sensors and smart control algorithms, which automatically radically expands the flexibility and application space, as we have also seen in Brian's talk. If you want a hybrid human-robot future and realize the vision of a true collaboration between humans and machines, and humans and robots in particular, the trick is to get humans and machines speaking to each other. Quite a long time ago, in 2012, Romana Rust, a long-term colleague and collaborator, and I, we were playing around in the architecture faculty in Vienna, the digital fabrication workshop there. And we were both, which is the first robot that we got, and we were both caught by a fascination for robots, but not merely for automation, but more as an interactive tool. We basically envisioned robot as a co-worker, an extension of people. And to basically explore a bit in that direction, we developed a system that we called SANS, which is the acronym for Sensor and Actuator Network. We kind of wanted to make this kind of without borders, or communication without borders. And in this system, people and robots would be connected via various sensors like a camera, iPad, or 3D digitizer, bringing information from the physical world to the digital model, and then robots as actuators, basically bringing information from the digital to the physical. And this was, for us, a way to establish a possibility for people to interactively take part in the fabrication process by basically designing during fabrication and influencing and moderating as digital fabrication would progress. We established basically a communication between different sensors and robot. We implemented a small server client application, which was written in Python. And it was a requirement to implement a very open and extendable system, which should be easily adaptable to any sort of devices. And in this application, a server delegates the data exchange between all the different clients over the network interface, and also incorporates a module with different algorithms for shape generation. We thought we were very novel at that time, and but after a few years, well, naive architects, we would say, we found out that this already exists in a way more mature form, and also developed basically all over the globe by a huge community. It's basically the concept of ROS, robot operating system, which we are very familiar with. However, our very small rudimentary system at that time allowed us to connect any sensor input with various CNC machines or robots, only with a few modifications. In this case, we tried out a 3-axis milling machine, where we tried the simultaneous milling of a 3D digitized surface with this 3D digitizer, where basically the milling machine was directly basically milling what we were scanning in real time. And of course, also this milling part would then basically cover the traces from your basically imprecise manual movement. So the question is, where can we put the intelligence? Can we not directly translate, but can we like kind of put some intelligence in between? So we explored fabrication processes using sensor feedback, which enabled some sort of complexity, although they were based on very simple rules. So in this case, we were like kind of pouring a thread on the surface, and we had a camera tracking this hand so that it could at any time intervene. However, if you were to stop intervening, then the fabrication would just follow some internal rules which we have been defining in some algorithm beforehand. And basically what we effectively tried was to combine the process of design and creativity with the process of making and computation. So, and also so that designs don't have to be frozen before, but could be developed during a process. In this experiment, we had a robot piling sticks, basically also not with a predetermined form, but only on a set of rules. This table was basically camera tracked from below so that the sticks that were placed on the tables could be tracked. And a user could define an initial state by placing a set of sticks on the surface for start. Here you see Ryan placing some sticks on the table. And then the robot's job was to assemble the sticks in a way that the stability of the whole structure is sustained at any time of the process. In the back, you see the projected screen showing the geometry viewport, which in a moment should show the digital twin, basically the objects that we track on the table. And then also how the algorithm is performing, basically looking like tracking newly placed sticks, measuring their length, and then finding a stable, basically new position on the stack. So you can see here, maybe on this side here, how the search algorithm performs. It's just a brute force searching, so sometimes it took a long time. So I guess a few years later we would have some better ideas on this. But basically the idea was to how can we have stability criteria or structural performance criteria embedded into the algorithm and still being able to kind of have some intervention during the process. Coming back to the topic of construction robotics, basically where I started from, I went to ETH to do my PhD. I have kind of left this question of human-robot collaboration, but it has proven to be very useful to apply strategies of sensor feedback and feedback-based adaptive fabrication to the topic of construction robotics. Allowing us to deploy robots not only in very controlled and structured environments, but using them for fabrication directly on building sites where basically mobility, perception, scene understanding, the topics that Brian was pointing out, and the integration with suitable design to fabrication workflows allows them to cope with uncertainties and unforeseeable events, and also with the materials in use. And it allowed us to realize projects such as mesh mold and in situ fabricator. In situ fabricator is this mobile robot in the background, which was basically a unique chance to prove that robotic in situ fabrication, so having robots build stuff on site, is not just a future vision, but in some constrained cases is ready to be applied successfully in a real world construction project. This robotic in situ process applies a novel construction system for reinforced concrete structures, which was named mesh mold. It is a process in which a dense steel rebar mesh is fabricated, which acts as formwork for the filling of concrete and as reinforcement after the concrete has hardened. This fabrication technology was specifically chosen to show the full potential of robotic in situ fabrication. It is fully load bearing. The process facilitates the construction of geometrically complex and differentiated, structurally informed and structurally optimized structures in both a material but also labor efficient way. Basically, you can get rid of formwork at all. This process was shown as part of this residential unit called DFAB House. It was a research building by the EMPA, the material testing facility of ETH Zurich in Switzerland, in which this bespoke reinforced concrete wall, which you can see here marked in red, provides the main load-bearing element to carry a cantilevering floor on top and then a two-story timber unit top. The unit was then becoming a house for guest researchers or temporary stays of researchers. For the mobile robot, we developed several generations of end effectors that can assemble a free-form rebar mesh through bending, cutting, and welding. And this end effector also integrated a complementary vision system, one for the robot's localization on site and one for surveying the fabrication at all time in order to allow the robot to operate basically autonomously, or at least that was the goal. So behind all this, there's always sort of also a design tool, which we created in order to create the shape of the wall. In this case, this design tool allowed us to locally undulate the wall to increase the stiffness, so to increase the structural depth, and therefore being able to really reduce the cross-section to a minimum to save material also. And also this tool also informs designers about potential design spaces or violation of maximum or minimum curvature criteria, stability criteria, and so on. And it also, of course, integrates all the fabrication data in the same data structure. The mesh is fabricated in vertical layers as opposed to horizontal 3D printing, such that the mesh expands in the direction of the movement of the robot, because we couldn't move it continuously. It's basically a like quasi-stationary approach where you would move, print, then move, print, and so on. And we could fabricate this wall now with 8 locations, the total length of it being 12 meters. And again, I'm coming back to the sensor system because localization was done in 2 parts. We had these fiducial markers on the foundation of the wall for localizing the robot, well, more or less plus minus 2-3 centimeters, I would say. But then in order to be really able to operate very precisely at the end effector, where you needed millimeter accuracy in order to perform this welding process, you also needed a sort of secondary survey system to track or to register this mesh geometry, and then also to compensate for potential deviations. So here you can see a little plot where we measured the deviations. Sometimes there were internal forces in this occurring through welding, which would be deviations up to 2 centimeters, where we would need to adapt the fabrication data to counteract this fabrication data. So also we had to enable sort of a constant as planned as built sort of alignment, and then also comparison, and then change of action basically. This again documentary shows the process from the moment of deploying the IF on site. You can see here it cannot walk, so it has to be brought on a container, packed, not well, as Brian was saying, not legs are superior to that, so we tracked wheels. You can only, of course, drive on flat surfaces. Again, you can see here last adjustments to the code, the fiducial markers being tracked. We had to do a lot of calibration, and then mesh being welded point by point. It's basically spot welding, where each layer is connected to the next with a little piece of wire, and then the layer-like buildup. The scanning of the mesh contour, which we would have to do every other layer to register the mesh, and then, as I have pointed out, this the act of collaboration, we as researchers were feeding the material to the robot. In the end, this mesh is so dense that the concrete can be basically pressed in from the side, which was the initial concept of this whole endeavor, is to really reduce the need of formwork, so the mesh can hold the concrete and give the concrete the shape. The accuracy of the fabrication was validated after by taking ground truth measurements after the fabrication was finished, and we found evidence that the deviations of the finished structure really stayed well within plus minus 1.2 centimeters in comparison with the CAD model, which is like extremely precise for construction standards, and which allowed to install this floor, this cantilevering floor done by Digital Building Technologies, installed on top of it. And you can see here the interface where it's like kind of each other with quite high precision. The slender wall geometry of somewhat 12 centimeters in cross section was then also taking the loads from the upper 2 floors, the timber unit, which was then installed on top. and covered with this like sort of translucent weatherproof pillow foil. So now a few years have passed since, but the question remains, what about, so like where do we go from here, right? And somehow the question remains, what about thinking of robotization, not only in terms of automating everything, but how can we revisit the topics of human-machine collaboration, first with new technology at hand, because 10 years have passed since, but also with new conceptual approaches. It has always been largely criticized that existing approaches to robotization usually aim at the complete substitution of human labor. And we know that the demographic change in the AEC sector shows a very clear need for an innovative, highly flexible and adaptive assistive system to promote human craftspeopleship with the integration of machine. And can we, by looking at these challenges more closely, create a better understanding of the role of the human in this age of automation, also reflecting back on us. So to turn to a more people-centered perspective, Augmented Brickworker project, my latest basically collaboration with Grammaticular Research, pursues therefore a radically different approach in the field of digital fabrication, namely by hybridizing machine intelligence with traditional, very traditional manual construction techniques. And we were departing from a seminal project, which was also done in 2012. It's a brick facade of the Gantenbein winery in Switzerland, done by Grammaticular, which was built by robots, prefabricated. And you can see that basically a picture is drawn with laying of bricks, because each brick has an individual, like basically placement or rotation, which just allows to kind of create these pixelated graphics. And we took this project as a major source of inspiration, but we looked into if we can move away from robotic manipulation towards manual operation, in which we guide craftspeople by intelligent augmented reality tools and sensor feedback to gain basically such robotic precision. For this, a colleague of mine, Tim Sandy, a robotic scientist, also a long-term collaborator, took the sensing system off our mobile robot and developed a technology which allows to track discrete objects with a known geometry in space with a very high precision. And instead, basically of using it to control mobile robots, in this case, it is used to give visual instructions superimposed on a video feed to humans to enable them to build complex shapes. So I'm going to play this video. I hope you hear the sound.
In this sequence, a simple brick wall is built using the tracking system to guide the placement of the bricks.
Yes.
The desired geometry of the structure and the building sequence are pre-programmed into the system. When the user is ready to place a new object, the desired position of that object is projected in red into the images. Because of the accuracy and smoothness of the tracking estimates, this provides an intuitive reference to guide the user.
So basically that's a principle. We took this principle and we investigated its use to interface with bricklayers who are capable of doing the traditional craft of bricklaying with mortar. And by translating the craft's principles, such as knocking the brick into the mortar, to interactive visual instructions for manual actions. And we upscaled this technology for the construction of a brick facade for another winery, this time not in Switzerland, but in Greece. Also this video summarizing basically the project. So you can see here, this was the raw construction site. It's basically a frame of concrete pillars, and this is the already finished wall. We initially envisioned not a two-person use, but a one-person use where the sensor would be carried by the bricklayer itself, but it turned out to be too difficult or not robust enough. So we turned to a two-person job, basically, where one person would track the bricks and the other one would put the mortar and knock the bricks into place. And you have to be seeing these arrows in the picture. According to these arrows, the bricklayer knew where and with which force to knock, and then to basically have the brick very precisely where it was intended to be according to the digital model. And then we had also other teams starting to learn the system, so it was basically 2 teams working in parallel, filling up this total 9 fields. Then in steel beams were security, safety background, and this kind of drone view from the outside and from the inside. And also here the attempt was to kind of draw sort of this wavy image at the fields of bricks. Kind of the idea to reflect the surroundings, which is this like nice hilly brick vine hills. Yeah. So I'm already almost closing my talk, but I want to show one last project. It's a work done by Lydia Atanasova in our lab that investigates new collaborative workflows between humans and robots. Again, trying to combine or going down the road of combining explicit machine intelligence with implicit human knowledge and creativity. Again, here we're using an object tracking technology and also augmented reality technology, which allows 2 users and a robot to collaborate in the assembly of this little timber structure. With alternating physical actions. So both a person can place timber elements and robots can place other elements in response to the actions done by the person. The project also challenges the notion of a linear design to fabrication workflow where all design decisions are made prior to production. Again, we're looking into traditional craft processes. This was a process, column making, what was described by a researcher from MIT, Terry Knight, in 2017, where she's also basically observing the process of making as a set of following some set of rules in advance, but then also making decisions through sensory perception. Craftspeople can adapt their process flexibility, for example, to pursue new ideas, take errors into account, or to address some material properties which could not have been foreseen in advance. And she was describing this in sort of a rules of making grammar. So instead of thinking of shapes, you're thinking in processes, and also into how can we, basically codify them. So we're proposing this non-linear digital fabrication workflow, an open process which allows design ideas and decisions not only to be done before, but also during fabrication. This is a video which shows, again, the process. It's a collaborative workflow between this robot and these 2 humans, where one human would have a tracking advice to digitize human actions, and also the robot to intervene in between. We developed sort of an assembly grammar where through the augmented reality interface, a user could always see by being visualized these arrows where a structure can be continued to be built. In this grammar, elements are grouped into models of 3. The first element of the model would be placed by a person. So this we would call the user input. And then 2 subsequent elements completing the model would then be placed by the robot in response to the placement that a user would perform. We implemented this workflow quite pragmatically. So the process starts first by a user placing an object, and then this object needed to be digitized. For this, we use this mobile interface, which would allow to track the structure in space. You can see here the phone is pointed towards the structure and the edges are tracked and then aligned with the digital twin. And when the structure is registered correctly, the existing structure, then the digital twin is basically snapped onto the built timber structure on top, and the user can move the phone around freely. You can see here also superimposed the arrows indicating the locations where the user could continue building. As we have done that already, we must sync the previously manually built element with the digital twin. So this is done by pressing add object, so the user can add a new object to the scene. It has also to be placed approximately at the right location to give it a good initial guess. And then the object is tracked precisely. The information is fed back to the digital twin. And in response to this registered element, which is shown here in red, the design algorithm has computed 2 subsequent elements. And the robot is basically calculating the pick and place trajectory and then also placing the object. I hope you could follow, because speaking of interfaces, it's a step-by-step approach trying to digitize manual actions so that a robot can manipulate in an updated world of their own, basically. We assembled then a structure from the 3 different locations of the robot arms, and then in turn taking actions between people and the robot. We placed or assembled the structure according to this sort of growth algorithm. This is the digital twin of the fabricated structure. The red color here indicates the elements assembled manually, and the blue ones, the ones assembled robotically. The red ones here are the freely placed elements by the user, basically serving as the input. And then also the tracking accuracy, which was observed to be somewhat around ±3 millimeters. Accurate enough for the robot to operate within that space. Again, this structure is open-ended, so if we were to continue building, this is just a preview of how it could have looked like if we were to continue that. Yep. So in conclusion, let me briefly restate a few main points I was trying to raise or argue for. So while there are many technological challenges ahead, these works and experiments try to formulate an alternative vision of a fully automated building design and fully automated robotized construction. Instead, mainly in our lab, we are trying to proclaim the idea of a hybrid and mutually augmented human-robot work team, which could form the basis of a paradigm shift within the field of architecture and digital fabrication. We want in the future to provide greater flexibility, design freedom, an increased application space, and also we care for social sustainability at the end. So thank you very much. I hope I could spark your interest in that field of architecture and digital fabrication. If you're interested in more of our work, please visit our webpage, and you can also follow us on Instagram. Thanks very much.
Thank you so much, Catherine. That was amazing. Such a broad but also in-depth overview of a lineage of projects. Some of them I don't think I've seen before, and it was really, really lovely to see them.
Thank you. Yeah, it's kind of hard to go through the jungle in trying to phrase a somewhat coherent argument, and it's also an attempt from my side to start to try to kind of pulling the strings into one direction, because field is broad.
Yeah. Well, I think there is a clear kind of direction in which you are moving in. And I think that is also very much in line with what we've heard from Brian today, that there's a lot that we know about robots, in particular in this field, both kind of in our digital fabrication field from the perspective of architecture, and generally in robotics. But when that moment when you start interfacing with humans, that is where a lot of kind of unknowns and really interesting things happen. A few things that I would like to kind of bring into focus rather than ask, I guess, is some of the overlaps that I'm noticing in both of your work, which is somewhat intentional, and that is why we have the two of you here. It's my secret plan. But it's really interesting to see how, well, on one side, both of you have such a strong focus on what is actually happening on a real site, which I think is, again, not necessarily the conversation that the majority of the field of architectural fabrication and robotics construction is really concerned with. And I really appreciate both of your insights into what that actually means to get the robot onto a real messy construction site, and what are the challenges, and how many sensors are necessary, how many kind of new workflows must be implemented. And on the other side, of course, this focus on the human, where I think generally we are slowly moving away from this idea of let's just automate everything, and robots are perfect machines for doing whatever it is we tell them to do, but really towards this productive collaboration and productive combinations of things that humans are really good at and things that robots are really good at, and how do we combine them towards processes that are really, really useful. And there is a question that I'm pulling from the chat from Nicholas Sinclair that is very much in line with what I'm thinking, and the question that I was initially planning to ask. And the question is for both of you. Feel free to jump on it in whatever sequence you like. Do you think swarm technologies, both swarm algorithms and swarm robotics, will play a role in the future of construction robotics, for instance, the heterogeneous fleets? If so, how do you envision people might interact with these large-scale systems?
Yeah, I think, the distinction of swarm technologies versus just lots of robots is the idea that they're not aware of the broader task, and that they're doing discrete, smaller subtasks there. We've kind of seen that with Spot. I mean, you could argue that many spots pulling a truck, which is one of our earlier videos, is an example of that sort of thing. We have one little blip of a clip in one of the videos where somebody is riding a platform that is actually a Spot hexapod. So what is that? 6 times 24, a 24-legged spider. So there are things where obviously each robot only knows its subroutine, and that contributes to some higher level tasks. So yeah, I think so. I mean, for me, one of the more obvious use cases there was to look at what's going on in the entertainment industry with small drones and light shows, and to think about the ability to send several small drones with small cameras and limited payload and battery life to cover a large area as a data capture exercise. So I absolutely think that will play a role. I don't think it'll necessarily be like lots of tiny nanobots like swarming an environment. I actually just think that will be a common paradigm of how we network multiple robots together.
Yeah, I can only agree to this. I mean, I see swarm technologies. I mean, there's always a little bit of bits and pieces of swarm technologies. Also, if you want to coordinate multiple entities working on one task, right? The question is, do we have one centralized model? I mean, there's also this, even ROS operates on these two levels, right? The version now is that you have this centralized communication platform, but there's also this other kind of stream where some people try to develop this kind of stream within ROS to not have this central server where the whole graph is, you can plot the whole graph, but you can only have local information of your communication would not be routed through one central, basically, communication server. That already tells how, I mean, just this software architecture already tells you how the communication is performed. And I think in that case, I guess both is true, because some parts we will, you don't, not for every task you need to have all the information at hand. But for the person, that comes back to the person, sometimes this level, I mean, I think there's this company in performant. I think they talk about this terminology of observability. This is how can you cognitively make sense of a situation. And therefore you need to have little bits and pieces of information at hand to have a coherent overview of things. And then if you have a robot manipulator not having this notion, but just needing to do a subtask, then that's of course fine too. Yes, both is fine.
Yeah, and Formant and Rocos are actually two companies that, are already building robot fleet management software and supporting Spot, but supporting Spot in the context of lots of different types of robot. Essentially, what is the PLC for remote operation of mobile robots versus fixed robots in a factory setting?
But what we are definitely moving towards is this sort of scalability through multiple operations parallelized and then also coordinated. And then Brian, you have shown this one figure with a lot of data platforms. I mean, this already shows this like massive problem of interoperability, something that is maybe like it's an engineering problem you would think, but I think it's not as much as a research problem as an engineering problem.
It doesn't even factor in what's required for true like operational digital twins, which just times 100. Yeah.
Times 100. Yeah.
I think it's also really interesting, Brian, what you were saying around the 3D versus 2D scanning of the environment, that your machine can do 3D, in a pretty easily, like all of the technology is there, but it's still questionable whether or not it's actually necessary for the workflow processes that already exist on construction sites.
Yeah, we can't just push technology on the industry just because we think it's the right technology, right? It actually isn't for the way that they're doing business, and that's something that I enjoy being constrained by versus my prior role as a researcher is I enjoy having that pressure to add value today. It's like, yeah, I want to speculate on what's possible later, but it is interesting to engage in what's valuable today. And that's how, I make that joke about, wow, AI and 2D PDFs, like really, is that, but yes, that's like hugely valuable. And there are things we can learn from that will transfer into the 3D stuff, but we can't just force new technology down the throat of a business model that can't create any value out of it.
Yeah. And I think there's an interesting connection also, Catherine, to the project that you showed with the manual assisted bricklaying, because that does augment that very traditional practice. But again, with just the correct amount of technology that is necessary to achieve the process. And there's just so much value in this approach versus something that we often see in, especially in academia, where it's like, why don't we create a technology? And then that's where that sentence ends, and the user becomes this very abstract, mysterious human. There's this lovely book, how people became users, that kind of describes this whole history of how we've started changing our language and how the user is, the perfect mysterious human that will do exactly what we as developers of technology want them to do, and we're not really asking them what they want. And I think both of you have outlined the alternative route in such a beautiful, valuable way. I want to jump to another question from Angela, which I think is also part of this conversation and is a good extension of that. And the question is originally posed to Brian, but I'm going to extend it to both of you. How often do you get requests to modify your SDK and interfaces? And in translating that to Catherine's work, how often do you have to kind of reconstruct your software and hardware structure for projects when you start on a new project? How much of it is like building upon, and how much of it is building from scratch?
Yeah, I think that when you're trying to create commercial value with robots, you inevitably have to also be a software company. You really have to focus on UI and UX because again, like without the Spot tablet software, you know, you'd have all this incredible technology on your site and just no way to leverage that as a user. So, I mean, I think that's also a beautiful thing about being a hardware company, is that you can essentially have the same hardware stack providing value for years and years, but you can continue to unlock new behaviors on top of that. And, you know, even just the notion of autonomy, right? You know, when you're just focusing on the robot itself, there is no autonomy. That's a stack added on top of that robot that allows you to modularize it. So I mean, my biggest job is making the interface better based on customer feedback. Improved autonomy, but also improved autonomy with the right user interactions that make that worthwhile and make that usable. On the side of the SDK, you know, that's a collection of all sorts of stuff. I'm, you know, getting more documentation out there about what already exists, creating more samples in the Python client, which is a very user-friendly language on top of our gRPC protos. And there's no ROS, so I get that question a lot. ROS doesn't really scale with the types of things we're doing. That said, the SDK can be wrapped by others. We have people who've done .NET wrappers. We have Microsoft and ClearPath that both offer ROS wrappers, and that's useful to a subset of customers. And then in terms of the APIs themselves, you know, we just get customers asking for access to types of data that we hadn't considered before. So, I mean, the short answer is yes, constantly people are asking for changes, and that is part of being a software company, is being able to interpret those signals correctly. Because the other side of that is, you know, I get people asking for a spot that can do backflips on a trampoline. I don't think that's going to matter to anyone. Could we do it? Yes. Like, is that where we should be spending our time for something where we have revenue targets at the end of the year? No. So part of it's making the decision there too. You have to be careful around our engineers. You know, I came back from a customer engagement once and said, oh, this customer really wants Spot to be able to climb ladders. And at first everybody was like, oh, that's crazy, and kind of dismissed it. And then there was like a 5-second pause, and then everybody started jumping in with like, oh, actually all you'd have to do is X, Y, and Z. And it's like, no. Like, that is not where the core value of this robot is right now. Like, so we constantly have to prioritize those decisions. And it's really cool to be able to work with a team that could basically solve any problem. But I also love the constraint of how do we make this a business? How do we make robots practical for the real world so that we can scale their use?
Yeah, we are researchers. We never want to do things twice. But I have to say, after years and years and years of like reinventing the wheel, I mean, there are things repeatable, of course. I mean, for instance, we do have we're working or trying to contribute also on this open source Python platform named Compass, Computational Tools for Architecture and Structure. It's a Python only standalone geometry kernel with structural design and fabrication dedicated software pluggable to this, totally platform independent, and where we are not trying to look into creating a standard like BIM constantly tries to do, but we are focusing on interoperability. So trying to enable data exchange between, well, in our case, because research network of roboticists, material scientists, structural engineers, architects, and so on, to enable a fast data exchange and integration and common research between them. So by having created this, it is already observed that things are more kind of better documented and better kind of methods are conserved, and then people can really build up on existing things. And then rather principles and methods survive, and then, you know, case studies exchange and so on.
Awesome. Thank you so much. We have a hand in our Zoom audience, and I would like to pass the mic to Navid to ask his question.
Thank you. Hello, everyone. My name is Navid Kehani. I'm a PhD student in the Department of Civil and Mineral Engineering, and also UTIS. So I'm working under the supervision of Professor English Scholik, who's here, and Professor Brenda McCabe. So I really enjoyed both talks. But Brian, what you guys are doing is amazing. And what I'm doing in my PhD is totally aligned with what you guys are doing, with the exception that you would like to use drones. Yeah, so I have two questions for you. One is about repeatable autonomy in construction environments. So as you mentioned, indoor construction sites are dynamic and ever-changing environments. So how repeatable autonomy and I assume teleoperated mapping can handle this rate of change in the workspace? And the second question from you, who has many years of experience in the industry, I would like to ask your opinion about the main barriers in large scale adoption of robotic platforms like Spot in the industry. So do you think, is it the technology, is it the cost, is it the culture of the industry? Thank you.
Yeah, those are great questions. Yeah, in terms of autonomy so we're just talking about interior commercial construction environments, which are the craziest ones. There are a couple things. One is that, the base Spot platform is vision only. It's using cameras and sensing depth from that. That will not work in a construction environment at this time. No matter what Elon Musk says, you need LiDAR, you need an extended field of view. Part of that is because a lot of these environments have feature deserts or large open areas. Part of that is because things are changing, so you want to increase your chances of capturing features that don't change, like the core and shell or the structure, so that there's some kind of recognizable edge as everything else changes around you. In addition to that, you can use other localization methods. That is also modular through the SDK. One thing that we've implemented, for example, is April tag fiducials to allow you to localize to a set of fiducials. And that is actually how you initialize a mission. And then you can add additional ones. If you have like tricky areas, you can basically add that as an action. So I said an action could be a little dance, an action could be capturing a scan, an action could be localizing to a fiducial as well. And that kind of strengthens your likelihood of Spot finding its way, particularly useful in feature deserts as well. Which also points to the fact that the architecture of that is structured as such that over time you could add different localization sensing and then the ability to determine which thing is going to work best. So for example, when you take Spot outside, you don't necessarily want to use these kind of SLAM-based methods. You want to be able to benefit from like GNSS and your access to satellites. So you can switch to that, but then maybe you're in a solar farm or some other exterior environment where you're going under infrastructure and then you're dealing with multipath in GNSS. So maybe you want to switch back to feature recognition from perception systems. So we wanted to build something that didn't rely on external systems initially, because we knew that initially this was going into these human purposed environments, but then we wanted to build other things on top of that. Now, all of that said, there's still going to be a change you're going to make on the site that is going to necessitate a new mission. Eventually you're going to add partitions and things like that. So Spot doesn't need to be magic and move through walls. You could just say, I'm going to, do this relative to my construction schedule. So part of it is also common sense concept of operations. If you run a lean site, for example, you might have a demarcated pathway that's always kept clear of materials. Those unfortunately are few and far between, even though they're super useful for both robots and humans. So we also knew we needed to build in mission level options, essentially, to allow human intelligence to step in when necessary. So for example, Spot might say, I can't, or message you, not say, Spot might message you and say, I can't reach this targeted data capture spot. Like, you expect me to be within, X centimeters of this. I can't get there because there's something in the way. What should I do? And you can just say, well, just take the photo from where you are, or skip it entirely and move along. That's an example. Another example is there's a scissor lift or a wall in front of me that I've never seen before. Would you mind piloting me to the next location? And when you're in the interface, you get a kind of augmented overlay of the recorded path. So you can get spot back on its path to a place where it will recognize features again and then set it on its way. So we recognize that it's not just about dynamic environments, it's about unpredictable environments. The things I have seen on construction sites are bananas. It's just really hard, no matter how well you run a site, to be able to go in there and predict. So we also want to have common sense tools that allow you to assess the site on a regular basis and then build flexibility into mission decisions and mission planning.
Awesome. Thank you, Brian. I think we have another raised hand from Nicholas.
Yes, thank you. These were excellent talks. As a first-year student, this is an incredible opportunity, so I'm really enjoying this. But in terms of your experience implementing user interfaces and user experiences, I know, Brian, you just talked about, if Spot, can't reach a place, like it sends you a message. But in terms of that sort of human-computer, human-system interaction, what are some of the most effective methods you found from your experience using them, and potentially speaking to some of the methods that didn't work quite as well and what you learned from that? Thank you.
Yeah, I mean, we have a culture of engineers that some have been working on these problems for decades and not on commercially selling them and creating good software. So you kind of have this default instinct to add a Python GUI with like 400 checkboxes. That's fine for a pre-release and user testing, but everything has to be contextual, right? So if I'm in the middle of playing back an autonomous mission and I decide I want to add a new action, I decide I want to scan in a room that wasn't there before, or I decide when I get to the end of that mission, they've now poured the rest of the slab and I want to continue the mission and record a new segment. Those can't be like buttons that are just always in your face, but they also can't be hidden away in a menu. So I think context-based feature sets have been great, but also there's limited real estate in that tablet too. You're often using that tablet to see through the various cameras of the robot. So you want to make sure that you're using that real estate space wisely. I am not an expert in this area, but I've learned from our team, and I just can't stress how important it is enough, and how that's a big part of the cultural shift of a kind of robotics research company to a commercial robotics company, is to really give that the attention it deserves. Again, you can have the most incredible robot, but you're not going to win the market if you have a bad interface.
Thank you. I think we have another, not a raised hand, but we've talked about it in the chat. Xing Chang, I'm sorry if I'm not pronouncing your name correctly, but I believe you wanted to ask a question with voice as well. Or not.
I think your hardware is muted.
Yeah, we do not hear you.
Oh, technology.
I see it's typed into the chat.
Yes, I guess I can also read that from the chat. The question was, what are your visions for robots that can do interior or landscape design constructions, like painting walls, installing doors, windows, pipelines, planting trees and flowers, preparing earthworks?
Catherine, are you familiar with the people working on the HEAP project and the landscape chair? That might be interesting to discuss.
You mean the excavator project? The other scale?
In terms of like automating earth moving and landscape design as an extension of that.
Yeah, I mean, I think all of these topics that you have been now raising here, like landscape design, construction, painting walls, installing doors, windows, pipelines, planning trees, flowers, preparing earthworks, they are all physical manipulations. They can somewhat or in some way sometimes can be grouped as to assembling discrete objects, or earth moving would be like sort of malleable, like manipulating malleable material. Or if I see painting walls, then it's not so much about manipulation, but rather of context, like just applying something or forming. So the expert here is actually Maria in this case, as she is working on this. Where is she? There's like two, let's say, streams of thinking there. One is like this task-specific robots. So we will design a robot for each of these tasks, which are in some case very specific. The other one is to really create a very generic machine that can, just by exchanging the end effector, can do any of these. I guess it's all about being able to really manipulate physical environment, and that if monitoring is already that hard, you can imagine how much harder it is to then actually manipulate. And I guess we are moving there, but the road is bumpy. And you have been basically discussing this construction site, or mentioning this robotic construction sites from the 80s. So we're not the first generation working on these topics. I think we're now working on a different level, because we have, of course, AI, we have like totally different accessibility to these technologies. And now it's like in the 80s, they basically tried to recreate these factories on a building site. So they had this very large scale and huge kind of artworks, I would even say, of massive steel constructions that would then perform as a robot level by level. I mean, as what we're seeing here is more like going into more small scale, agile, mobile manipulators, which can move around somewhat similar to people. I guess for construction, then we want to raise their kind of payload capacity, so to do very heavy load work as well. But yeah.
Yeah, and I like to ask the question, because this is just kind of like, what's your vision for the scope of all the things robots could be doing in construction? And I like to constrain that a bit by speculating on what can be done off-site with industrialized construction methods, and then what's left to do
on site
in the field.
Yeah, I mean, that is the second thing that we have now, these huge companies which are trying to install prefabrication like at massive scale. I kind of also doubt that it can be applied to everything, right? We have materials which we don't want to ship to a plant and then ship it back to the building site. Maybe we want to like reduce transportation of materials. If we have these huge centralized plants, then we like increase transportation massively. And then not all materials can be reworked in prefabrication, right? If you think of like brickwork, like it's very hard to transport brickwork, right? It's something that you have to like, I mean, people or companies do it. I mean, they do it more and more. They have this element construction, so they prefabricate the whole elements, but they have to secure them for transportation extra, something that they would not need if it was built on site. And then installing, of course, like if you think into prefabrication, all of these doors, windows, pipelines are pre-installed, but that again, it doesn't apply to each and every case, right? And then I think, again, this will be a combination of both. I would put on each of these decisions, I would just put the question of what is more kind of resource efficient in a way, to kind of also look at that note, because we are making very stupid decisions, or have been making very stupid decisions, just because it's simpler or just more comfortable in a way also. But maybe we really have to calculate very precisely what makes most sense in that case. Yeah.
Yeah, I think there's some interesting examples too of finding middle grounds, like where the one I love the most is the idea of like 3D printing through some kind of material deposition with robots versus bricklaying with, you know, human size bricks with robots. And then you have something like the FBR Hadrian X robot, which kind of finds an interesting middle ground, which says I'm additive, but it's still modular, but the module has been designed specifically for what this robot is capable of. And I'm also targeting CMU, you know, single story residences, gas stations, commercial constructions, like a very common way of building across the world that is a kind of more limited set. I think, Catherine, one of the things that you deal with in academia and with the design consideration in particular is the idea that robots can help us expand the design space. So I think there's kind of a subset of people who are very like business driven, who are just like, I want to use a robot to do things the way things are done today to make more money.
Exactly. Yeah. No, that's the most interesting point, like what you're raising here, because we have to. I mean, I don't know if I have maybe not emphasized it enough, but these processes are completely they're completely thought new from scratch, right? These processes, like assembling this reinforcement mesh, this process that has not been existed before. It has been thought through the logics of robotic fabrication. Again, Maria's work is somewhat also going in that direction of creating this material robot systems where one is like kind of complementing the other, and they are thought in combination, and they cannot be thought without, right? And if we want to, like, I think that's also a big hurdle, which is that's why we have to basically think of these processes from the design and planning side, because we have to think through the logics of these technologies in order to be able to like come up with like efficient and innovative solutions in that sense. Because in the end, we cannot just automate what is, as you say, it doesn't in most cases, it's not really efficient to automate what is existing and what has been done with different logics or thought with different logics. We have to think, completely rethink these processes in order to make them somewhat working also. And this Hadrian is, I think, is also a tremendously interesting example in that sense. Yeah, like, because they really also recreated something that worked through the logics of their kind of system that they envisioned. Yeah. So these questions are not just rooted in technology; they're like rooted, like they're kind of, they have to be thought. That's why this research is so important to be done in interdisciplinary manner, right? So that we kind of come from all these different sides and like, look at this from different perspectives, and then come up with brilliant, innovative new things.
Thank you so much, Catherine. That is such a perfect kind of wrap up sentence that we should be doing more interdisciplinary research. I do have a tiny kind of cheeky question for both of you. After this conversation, will we be seeing projects with industrial robots and spots and humans? And how do I sign up for that?
That's a great question.
Great party.
Yeah, I mean, it's been interesting to see which academic programs have purchased Spot. It's not architecture and design. I don't think they can quite make sense of it if it's not directly building something. And manipulation is, I think, the next phase. The academics that have really latched onto it are those in kind of construction management and administration programs who understand the value of the data capture and the kind of ubiquitous environment sensing, as well as looking into the specifics of like safe operation and things of that nature. Maria, you and I have had many talks on which types of robots make sense with other types of robots. You know, is the building a robot? Are components roboticized? Do we just have more interesting tools that work with existing materials? It's kind of a mind-blowing spectrum. So I think the important thing from a research perspective is to not get stuck in the rut of fixed arm, you know, established paradigms, right? Fixed arm, and now it's funny to think, you know, legs, an established paradigm. Who knew? to continue to kind of think along a spectrum of possibilities. I think Catherine talking about these ideas of material robot systems is something that's particularly important when you're designing robots specifically for construction, because another thing we're seeing robots that weren't designed for construction being adopted into construction. There's nothing wrong with that. It has provided a certain amount of value and has allowed those professionals to build off of the work of other professions and is kind of interdisciplinary in nature. But I think part of the work of researchers in that space is to also think about those material robotic systems, to think about new morphologies that are very specific to the discipline. I don't think we've truly seen that, and maybe that's because it doesn't work, but maybe that's just because we haven't put the right things together just yet.
Awesome. Well, thank you both so much. In the interest of time, I do have to wrap up. I wish we could continue having this conversation for the rest of the day. Thank you so much for participating and joining us for this afternoon. Catherine, on your time zone, that is evening. Thank you for gifting us this time. Thank you for the audience, both on YouTube and here in Zoom, for joining in and asking super interesting questions. I know that some of the questions didn't actually end up being answered because time is always an annoying parameter, but maybe you can follow up with our speakers afterwards. Yeah, thank you all so much. And we will see you for our next talk
in May. David Scaramuzza seminar series. There you go.
Awesome.
You're on it. You're totally on top of it. You got this.
Thanks. I was like, no, I don't have the document prepared.
I know. That's exactly what happens to me too. Okay.